Hey y'all, today we're going to be talking about exponential functions. Today we're not really going to get into a derivative, but we're going to get into what is an exponential function. Now this is a natural thought because what we have been talking about were polynomials and rational functions, i.e. functions that are coefficients and powers of x, plus blah 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 blah. Now a natural question would be, what if I flip-flop the powers and the variable? This will lead us to functions that look something like this, where a is a constant and x is our variable. So without further ado, let's get into it. Now we'll begin with this function right here. So as an exponential basics, we'll start with f of x equals b times a to the x, where we are allowing a to be greater than 0, not less than or equal to 0, and b and x are allowed to be anything. Now, why do we want to consider when a is just greater than 0? Well, if we think of an example, for instance, what if we let a equal -2, and let's just say b is equal to 1. So b is a real number, a is -2. That would mean our function looks something like this. F of x equals -2 to the x. This runs us into some domain issues. For instance, I can't evaluate something like f of 1/2, because this would be -2 to the 1/2 power, which we all know, because we're getting good at this, is the square root of -2, an imaginary number. So therefore it's convenient to go ahead and restrict a to be greater than 0 to avoid these types of issues, so we can let x be any real number. Now what is b? Well, b actually ends up being our y-intercept. Remember that a y-intercept is just what happens when x equals 0. So if I were to plug in 0 to any of these functions satisfying this, I would get b times a to the 0th power. But a to the 0th power, since a is greater than 0, will actually just be 1. So I just get b times 1, or just b. So, helpful to think about, b is just your y-intercept, and a is just going to be greater than 0. That's going to end up kind of giving us indications on which direction it's going and how steep or shallow that graph is looking. Now we begin our discussion of what a really does for our function. So let's start with the exact same scenario. Let f of x equal b times a to the x, where a is greater than 0 and b is any real number. Well, since a is greater than 0, we can actually split that into 2 and let's say 3 cases. If a is greater than 1, then f of x tends to be increasing. So our graph will actually look something along the lines of this, where right here is the point 0, b. If a is between 0 and 1, strictly, then f of x is actually decreasing. So you can kind of think about flipping this picture the opposite way, where we're going downhill along that order. Where, yet again, this is the point 0, b, because always if we plug in 0, that a will go away. Now the reason I was a little wishy-washy earlier is I'm leaving out one case right here. What about the case where a equals 1? Well, in the case of a equals 1, our function becomes f of x equals b times 1 to the x. But now hold up. 1 to any power is just going to be itself. It's just going to be 1. So that means my function is actually just the constant line f of x equals b. A flat line at the y value of b. So although technically we could consider this maybe an exponential function, we usually don't worry about it because it just leads to a constant function, something that we've already considered. Now you might have noticed something in the last slide that we had up. When a equaled 1, we had a perfectly flat graph, a constant graph. We can actually generalize this a little bit. Given f of x equals b times a to the x, where a is still greater than 0 and b is any real number, we actually have the following. The closer a is to 1, meaning as I creep up to 1 from either side, the shallower my graph will get. The flatter it will get. The closer to that constant graph it will get. The opposite's also true. The further a gets away from 1, as we creep away from 1, the steeper the graph gets. To visualize this, let's go ahead and graph the following functions. F of x equals 2 to the x, g of x equals 3 to the x, h of x equals 1/2 to the x, and j of x equals 1/3 to the x. Starting with both of these two. Now remember, and actually one thing to notice, is that in each of these cases, b is equal to 1, meaning our y-intercept will occur at 1. Now, with these two cases, we have a is greater than 0. 2 and 3 are greater than 1, meaning our graph is going to be increasing. Now, starting with 2 to the x, maybe that graph looks something like this. Through our y-intercept, and up. Now g of x, which I'll draw in red, that's still greater than 1. A is greater than 1, so we're still increasing. However, it will be steeper, meaning it will look something like this. Still going through there, but we overtake it when we go towards positive infinity. We become steeper. Now, if we do h of x and j of x, we'll actually see something similar happen. So, for instance, graphing h of x in green, we have 1/2 to the x. So 1/2 being between 0 and 1, we're going to have a decreasing function. So maybe we look something like this. Now we're still going through that point 0, 1 because our b value is equal to 1, and that is our y-intercept. Now bear with me here, I'm going to have to do blue again. If I graph j of x in a blue dotted line, we notice that first off a is between 0 and 1, so we're decreasing. However, it is further away from 1 than h of x. So I'll actually be a steeper graph. So this graph will actually look something along the lines of this. Where I tend to be steeper on the left-hand side. So these are kind of the relationships that we can start to generalize. And actually, come next slide, we'll see a pretty cool relationship between f of x and h of x, as well as g of x and j of x, if you don't like working with fractions. Now let's talk about how we can see maybe a relationship between a, if it's between 0 and 1, and a greater than 1. So first off, let's pick up with h of x from our last slide. 1/2 to the x power. If you wanted to, you could actually find a way to convert this where a is greater than 1. To see this, notice that 1/2 can be written as 2 to the negative 1. Remember that you can always make it a negative power by just bringing it up. Well, hold up. Now I have a power to a power. I can go one step further and simplify this as 2 to the negative x. Now this is actually inversely related, meaning it's just a reflection across the y-axis of 2 to the x. So h of x equals 1/2 to the x, and f of x from our last slide being 2 to the x are actually just flipped across the y-axis from each other. Similarly with this new function k of x equal to 5/7 to the x power, I could rewrite this as 7/5 to the negative first power raised to the x power. Now what this will give, since I have a power to a power, will be 7/5, now a number greater than 1, to the negative x. This hopefully lends credence to why you're decreasing when you are between 0 and 1, because I pick up a negative right here. This trick tends to be useful more in this situation, so you can kind of visualize it being opposite of things when the fraction is simple. However, it applies to any number between 0 and 1. Now that we've got a general feel as to how these functions look on graphs, let's talk about a little bit of algebra and how we can actually solve for the function if given 2 points that lie on the graph. So, for an example, find f of x equals b times a to the x, where we're still assuming the same things about a and b, if 0, 2 and 2, a lie on the graph of f of x. The biggest thing you're going to look for is if you have a point with the x-coordinate being 0. That's going to be a dead giveaway for what b is. Because remember, b is just the y-intercept, and the y-intercept occurs when x equals 0. To see this more concretely, what we could say is given this point, we know that if I plug in 0 to my function, I should get 2 as an answer. However, if I actually just plug in 0 to this thing, b times a to the 0, I could actually simplify out this right-hand side. Because remember, a to the 0th power, since a is greater than 0, will just be 1. But, now noticing what we've written, 2 equals b, we have what b is. b is 2. Now in order to get a, we actually have to use this other point, 2, 8. But we're going to do a very similar thing to what we did right here. If I plug in 2 to my function, I know that my answer will be 8. Now if I actually plug in 2 to it though, plugging in 2 for b, I'll have 2 times a squared. Plugging in 2 for b from this line, and 2 for x from this point right here. But now I have a formula I can solve out. So for instance, if I divide by 2, I'll get that 4 is equal to a squared. And ultimately, that a, just from the algebra alone, could be plus or minus 2. The kicker, the thing that will actually allow me to say just positive 2 in this case, will be that we're requiring a to be greater than 0 in this chapter. So none of that negative business. Therefore, my function, f of x, better equal 2 times 2 to the x. And that'll be exactly my answer. And yet again, you could check that by plugging in 0 and plugging in 2 and seeing if you get the respective y values out. Hey y'all, thanks for tuning in today. Now as a quick recap, these exponential functions were useful in describing situations with successive percent increases and decreases. So, for instance, if we wanted to describe exponential decay, such as carbon dating, something that's useful in there, these are the types of functions we want to be after. Or population growth is a pretty common example of that. Now, the main thing that we went over today, besides just kind of how they work and what they are, was given f of x equals b times a to x. b is just the y-intercept, and a describes as best as we can the slope. If you have a word problem and you're trying to find this function, if you look for two points, you will be able to find this equation of a line. Now, next time we'll be talking about how to derive these types of functions. So stay tuned for the calculus. Thanks, y'all.